So the geometrical definition of limit which we gave on my previous lecture was that we say limit x tending to a fx is equal to L, where fx is our function, if there exists a epsilon neighborhood of L such that corresponding to this epsilon neighborhood of L, that is n epsilon L, there exists a deleted delta neighborhood of this A, where this limit is, where variable is approaching towards. So if there exists a deleted delta neighborhood of A for all the epsilon neighborhood of L, then you say that the limit exists and the limit will be equal to L. That way we have explained it, that in normal situation you can understand that the function value would be approaching towards a fixed number L when x is tending towards A, and the greater details we have explained it on that particular lecture. Now with this definition, see, and we have also proved two very important limits that particular day, and that were the limits of the identity function and the limit of the constant function. What we have shown is that see, this identity function and this constant function, their domain is the entire real line. So what we have shown that particular day, making use of this theorem, that the limiting value at any point of its domain, that is on anywhere on the real line, will be same as the functional value for both these functions, that is the identity function and the constant function. Because see, these two important limits, they will play a vital role in further proving the result that the limit of a polynomial is nothing but, again, it's the limiting value of a polynomial is nothing but its functional value at that particular point on which limit is being calculated. So this is all what we have done. Now, as I have been telling you that this is the geometrical definition, and we have also explained on that particular day two important identities. One was that mod this thing, that what this epsilon neighborhood of L will mean here in context to these symbols. So n epsilon L will be nothing but it will be your open interval L minus epsilon, rather you can write that this implies n epsilon L is this open interval, and this thing it's fine. So this is what you have to see, and then see this n deleted delta neighborhood of A. This is you are slashing it, and what is the element which you would be deleting from here is the middlemost point in reference to this particular definition, and this will be nothing but the same thing as A minus delta, open interval A minus delta, A plus delta minus A. The middlemost element from this open interval A minus delta, A plus delta, if you are deleting this middlemost point, then this particular set is better known as deleted delta neighborhood of A, and this is what exactly is here. So the second definition, which is not geometrical but of course conveying the same spirit, will be like this. So please do write down the second definition here, and that is that okay, I am rubbing it out. This thing you have to take into care. Okay, so this is the first definition, that is the geometrical definition, and the second definition which you will be encountering. See, this for having a visualization, this geometrical definition is definitely more easy because you can perceive the things through it in a more easier manner. So the second definition appears to be somewhat more abstract, and therefore, but see, both of them amounts to the same thing. So the second definition is like we say same thing, limit x tending to A fx is equal to L if for every epsilon greater than 0 such that mod fx minus L is less than epsilon. This is L whenever yes 0 is less than mod x minus A is less than delta. I would like to further emphasize that this inequality is nothing but the epsilon neighborhood of L, and this is these two inequalities. One is this left one and the other is this. These two combined will give you nothing but the deleted delta neighborhood of A. So this is the second definition, which is somewhat more abstract. But then see, when since all things have been explained to you very nicely, that what these two inequality conveys is nothing but deleted delta neighborhood of A, and what the element has been ignored from this deleted delta neighborhood of A is the nothing but the middle element A. And this is of course nothing but the epsilon. This first inequality is nothing but the open interval L minus epsilon to L plus epsilon. So this is the second definition. Now see that now one very important result which we will prove now will be that, see, you take any continuous you take a function whose graph is well known to you, and you want to show. So for that therein the function limiting value is nothing but the functional value. You can always show where, see, there is no abrupt change in the value of the function. There where the graph is continuous. Continuity, see, in a layman language means without any breaks and without any abrupt changes, like your modulus function. Suppose this is your modulus function. You know its graph is like this, and so this is the your this signum function, this greatest integer function, it has got breaks at all integral values. So you forget about it. But if you are considering intervals where this even greatest integer function is not taking integral values, then see what you can show is that everywhere the functional, the limiting value will be equal to the functional value. So here once again, see, I will take it up. Suppose you take any point. Suppose this is the point where you have to find the limit, and this point, this is the point, suppose A, and the functional value here, it is your modulus function fx is equal to x, fx is equal to mod of x, and this is equal to x if x is greater than 0, and this is equal to minus x if x is less than 0. So here, see, suppose here A is somewhat negative, so A takes the negative values, and its functional value here is what? This much of the, that is mod of A. Mod of A, that is minus A. Mod of A, if A is negative, will be what? Minus A. Because, so what you will do? You will first take a epsilon neighborhood of this thing. This is mod A plus epsilon, this is mod A minus epsilon. You will draw lines corresponding to here. Take this is suppose some other point, say x1, and then take a point to corresponding to this thing. Say this is point 8 x2, and let that corresponding distances be delta 1 and delta 2. This is delta 1, this is delta 2. So what you need to do now here, see, you had to, for this value of epsilon, you need to find a deleted delta neighborhood of A, around A, such that whenever x falls within this deleted delta neighborhood of A, then your functional value should fall within this epsilon interval of this mod A. And this is quite simple. What you need to do, if this is delta 1, this is delta 2, you take delta to be any number which is less than delta 1 and delta 2 both. And this will be your required delta. This, for given this epsilon, this will be the required delta. Because see, now what will happen? This epsilon neighborhood of A will fall within this x2 minus x1. That is A minus delta, A plus delta, This will be a subset of what? X2 and X1. X2 and X1. So what will happen? That whenever see X is lying here, what will happen? You can easily see the values will lie within this this epsilon interval of mod A. Anywhere here you can take it, because between x1, x2 and x1 the values are lying in the epsilon neighborhood of A. So obviously for a smaller interval within which is lying within the x2 and x1, see obviously the value will fall within it. So this is how a geometrical method for proving that the limiting value of modulus function is nothing but its functional value. Likewise, see, we have shown for all the trigonometric functions, see, wherever they are not having any abrupt jumps in the value of the function, therein what you will notice is that through this geometrical method you can always show that there do exist for a given epsilon interval of L, there always exists a deleted delta neighborhood of A. So this is the methodology and strategy which we shall be applying for all the trigonometric function, and that is why see we had been explaining you, like in trigonometric function you have seen 10x, it is showing a somewhat abrupt change in the value of in the functional values when it approaches the odd multiples of pi by 2. Similarly, you see other functions, cot x shows it goes one way plus infinity, other way minus infinity at all the multiples of pi. So these are the things which you have to take care of. Otherwise, in rest of the part, where see there is no abrupt, I repeat, and this thing you will bear in mind, that wherever there is the graph is continuous, therein always you can show that the limiting value will always be equal to the functional value. So with this understanding, see, now we take up another important result, and we will take quickly the properties of these limits, and these properties will go a long way in proving important results like the limiting value of a polynomial is equal to its functional value, or wherever you are having this 3-4 functions with plus minus sign and multiplications of two functions, etc. Therein see these properties will be too useful for you for finding the limit of such functions which are in the expressional form, where certain two functions are multiplying or dividing, or three functions, so few of them multiplying, few for dividing, and few adding and subtracting. So let us take the properties of these functions. So write down properties of limits. So the first property is, here see, we will assume that the functions are well defined, and before see I proceed here, one very important thing at the very outset I will be telling you is here, that all the functions which we will be considering here in the properties here, see therein what we will find is that the functions and these limiting values, all of them will be finite and bounded. Bounded, see this expression I would like to clarify here, that by bounded function we mean that suppose your fx is some function defined over some domain D. Then see throughout, and if there exists a real number, positive real number m, such that modulus fx is less than m throughout its domain. Throughout its domain, then see we say that the function is a bounded function. The function is a bounded function. So please remember this definition, that what we mean by bounded function. Bounded function means it is not, it can be contained within two real numbers. So mod fx is less than m, it also means that fx is less than m is less than minus m. So mod fx is less than n amounts to this inequality. In fact, both of them are same. Both of them are same. This implies this and this implies this. So this thing also you have to take into cognizance that all the properties of limits which we shall be now proving there in the functions and the limiting values, all of them will be bounded. All of them will be bounded. So with this, let us take the first property here, there will be a good number of properties. So what we will assume, we let individual limits of these functions exist. Let limit x tending to a f1x is equal to L1 and limit x tending to a f2x is equal to L2 So now see, obvious from here itself is that both f1 and f2, they are having the same domain. They are real valued functions. They are real valued functions. I have already told you the difference between real functions. In real functions, your range set is a subset of real numbers, whereas in real valued function, both your domain and codomain happens to be the subset of your real line. So this thing you have to understand. So here see, when we are saying that individual limits of these functions, when x approaches a, they exist. They exist and they are respectively L1 and L2. Further, see what thing it shows is that both f1 and f2x, they have a common domain. They have a common domain. Then the first property which you need to prove is that limit of the sum of two functions, limit x tending to a f1x plus f2x is equal to sum of their individual limits. Is equal to sum of their individual limits. That is, this is equal to limit x tending to a f1x plus limit x tending to a f2x. Important theorem. And likewise, this is not, even if it is minus here, so it will become minus. See, addition and subtraction, they are they are almost same operations. So first let me prove for plus, then see you can prove it for minus. And the second theorem likewise will be that limit x tending to a product of two functions, f1x into f2x. Is equal to product of their individual limits. Product of their individual limits. So this will be what? L1 plus L2. This will be L1 plus L2. This will be what? Limit x tending to a f1x into limit x tending to a f2x, and as such this will be equal to L1, L2. Likewise for this thing, third theorem will be that if you have the division of two functions, then the limit of this rational function f1x upon f2x, this will be equal to the limit x tending to a f1x upon limit x tending to a f2x, and this is nothing but L1 upon L2. Now here see, obvious it is that f2x will not be equal to 0 throughout its domain, and here it is xa, and L2 is also not 0, because if they become 0, then your here function will get undefined, here your limits will get undefined. So that is an obvious thing. I am not writing it, but that has to be understood. Now with this understanding, we will give the proof of this thing. They are too simple, only you have to simply make use of what has been given to you. And given to you is what? That the individual limits, they do exist. They do exist. So let us see how we can give the proof of them. So first is, limit of the sum of two functions is equal to sum of their individual limits. So how we prove it? Okay, and given to you is what? This top thing, individual limits exist. Okay, so what we have to show? So see, now recall your definition. What we have to show, that our function now this time is what? f1x plus f2x. This whole is to be taken as our function now. So this function and this limit we have to show to be L1 plus L2. So what we need to show is, so you say, first you do a little bit of simple arithmetic, and then see, we will again come back. A little bit of simplification is required, and why this simplification I am doing it, that will become clear to you, because see, my basic purpose would be that I will be some epsilon positive number will be given to me, and corresponding to this that epsilon, what I will show is that yes, there do exist a deleted delta neighborhood of what? A, where this variable is approaching towards, such that whenever x is the element of this deleted delta neighborhood of A, then my functional value, that is f1x plus f2x, will fall within the epsilon neighborhood of L1 plus L2. L1 plus L2. So for proving this thing, see, what I am trying to do is, please see a little bit of simple calculations. I am doing what? f1x plus f2x. Yes, minus L1 plus L1 plus L2, of course. This modulus, this thing I will show, this is less than epsilon. See, this will be less than epsilon, because epsilon is given, means this is this thing. But see, how to determine the delta? It has to be determined on the basis of this thing only. So this thing I can well write to be what? f1x minus L1 in one bracket plus f2x minus L2 in other bracket and modulus. Now this thing is nothing but less than equal to what? Modulus of this z1 plus z2 is less than mod z1 plus mod z2. So employing that result, this is f1x minus L1 plus mod of f2x minus L2. And this result I will be writing A. This result I will be writing A, because ultimately I will be substituting my value here. Now see, given to me is what? Given is that limit x tending to A, this thing f1x is L1. So this implies for every epsilon greater than 0 there exists a deleted delta neighborhood of A. Let epsilon be equal to epsilon by 2 this time. Okay, so here for this epsilon by 2 there exists, so this, if let epsilon equal to epsilon by 2, this implies there exists a delta 1 greater than 0 such that what? Mod f1x minus L is less than epsilon by 2 whenever, yes, whenever 0 is less than mod x minus A is less than delta 1. Similarly, limit x tending to A f2x is equal to L2. This implies what? For epsilon is equal to epsilon by 2, there exists a delta 2 greater than 0 such that delta 2 greater than 0 such that, yes, mod of f2x minus, this is L1 please, minus L2 is less than epsilon by 2 whenever 0 is less than x minus A is less than delta 2. So this is 2, this is 3, and then see what I say is that let delta be smaller than both these delta 1 and delta 2. Now see, and that will be my required delta, and that will be my required delta. So now see, what I am doing is that I am rubbing here so that you can see the things clearly. Okay, Now what I say is that even I will rub this thing and I will keep only up my equation A. Okay, and now see, now my contention is that my required delta, now my required delta is less than delta 1 and delta 2 both. So any number which is less than delta 1 and delta 2 both, it can be taken to be my delta. Why? Because if delta mod x minus is less than delta, will be less than delta, then this inequality will hold, because it is holding for delta 1, and mod x minus a is less than obviously delta, because this open interval will lie in this thing, and of course see, you are ignoring the middle point, and likewise this inequality will also hold good. So now see, putting these two values in equation 1, what we will get, putting the values of 2 and 3 in A, what we get, mod, yes, see, bracket, see, what we will get is f1x plus f2x minus L1 plus L2, it will be less than what? Less than, yes, please see, fx minus L1, now what it is less than epsilon by 2. Epsilon by 2, and then this thing f2, because this thing is equal to this thing. Mind it, and this thing is nothing but this thing. If you look in, before I rub it, then this result I derived from this thing only. So this thing is less than epsilon 2 by epsilon 2, which is equal to nothing but epsilon. So we have been able to show that whenever 0 is less than x minus a is less than delta, then this thing is always falling in the epsilon neighborhood of L1 plus L2, and therefore our result is accomplished. Similarly, see, we will prove for F1, F2. Similarly, we will prove for F1, F2. So same thing, some epsilon you will choose. Okay. So what is given now? Given is, again, individual limits exist. Limit x tending to a f1 x is equal to L1, and limit x tending to a f2 x is equal to L2. This is f2. Okay, individual limits are existing. They are having the same domain, and what you have to show is to prove is limit x tending to a f1x into f2x. This is equal to the product of the individual limits, that is limit x tending to a f1x into limit x tending to a f2x, and this is nothing but L1, L2. So see, same thing. What I will do, I will take like this, f1x, f2x minus L1, L2. I will write like this. See, let me simplify this thing so that you can understand why I am writing like this. It is what you do here. You write f1x, f2x, and then you subtract from here what f2, okay, f2x L1, and add it L1 f2x, and then rewrite L1 L2 minus L1 L2. So this thing is written this thing, that is you have added f2x L1, f2x L1 here, and this thing is nothing but this thing will be, now these two you combine at one place, these two you combine at one place. So this will be less than what? Mod of f1x, f2x minus f1x. Here f1x you can take common, and this thing will become f1x minus L1 plus mod of what you need to take common, L1, okay, and f2x minus L2. Okay, in other bracket. Because mod z1 plus z2 is less than mod z1 z2. This one thing is this thing z1 and this thing you have taken to be z2. Now here see again mod z1 z2 is what? It is equal to mod of f1x mod of f1x minus L1 plus L1 mod of L1 plus mod of f2x minus L2. This thing. Both things. So this thing we are writing equation A. We are writing equation A. I think it is visible both ways. Yes. Now what is given? This thing is given. Now what you will write here? Please see. You can write here. Say now. Okay. One more thing. What I will do it. Okay. Okay. We will assume that since we have assumed that both f1 and all these limits they are bounded functions, so we can safely assume that mod f1x is less than m, and likewise L1 is mod of L1 is less than m. Because all this function is bounded, so we can assume that there exists a positive number such that modulus fx is less than m. Likewise, mod all these limits are finite numbers, so mod L1 is m. We can always find a number m, positive number m, such that both of them are less than these things. Okay. Now see. Now since limit x tending to a f1x is equal to L1. So what does this imply? This implies that for every epsilon greater than 0, then so let epsilon be equal to what? Epsilon upon 2m. Epsilon upon 2m. So there exists a delta. There exists a delta 1 greater than 0 such that what will happen? Mod of f1x minus L1, this thing will be less than epsilon upon 2m. Whenever what? Whenever 0 is less than mod x minus a is less than delta 1. Similarly, see on the same lines, see limit f2x is L2. Therefore, again, if we take epsilon to be epsilon by 2m, then again we would be finding a deleted delta neighborhood of a here also. So similarly, so this is equation 1. So this is equation 1, and likewise we will obtain another equation on the same lines that mod of f2x minus L2 will be less than epsilon upon 2m whenever 0 is less than mod x minus a is less than delta 2, and this is our equation 2, and then our required delta be less than delta 1 and delta 2 both. So from equation 1 and 2, therefore a becomes how much? Yes, mod f1x, this is will be less than m, because mod f1x we have assumed to be less than m, it is a bounded function, and mod f1x minus L1 is what? Less than epsilon upon 2m, plus mod L1 is again less than m, and this mod f2x minus L2 will be less than epsilon upon 2m. So this is nothing what? mm goes and epsilon by 2 epsilon 2, so this is equal to epsilon. So what again we have been able to establish is the same thing, that given any epsilon, we are in a position to find a delta such that within that deleted delta neighborhood, whenever x lies within this deleted delta neighborhood of L, this our function, that is, what is our function? Product of two f1x into f2x. This is our function. So this thing will have limit L1, L2. L1 and L2 are the limits of their of individual functions f1x and f2x when x approaches to a. So our theorem is proved. So this is nothing So we have been able to prove that the limit of this thing is equal to. Likewise, see, we will be for this thing derivative. Oh, sorry, for division of two functions, we can show that their limit also is equal to the same thing. But there you have to be a bit cautious, because there you will have something in the denominator. Functions, if we, I can take it up quickly here. Same thing, given is what? Individual limit exists. Limit x tending to a f1x is equal to L1, and limit x tending to a f2x is equal to L2. This has been given, and you have to prove f1x. To prove I will be f1x upon f2x, yes, and this is our function. Limit x tending to a, this is nothing but limit x tending to a f1x upon limit x tending to a f2x. And here mind it, f2x is not equal to 0 throughout its domain. That is where our f2x is its element of domain. So it is not equal to 0. So now see, so what we need to do is see what our basic studies will be. We will be, since we have to prove this thing to be like this, f1x upon f2x minus L1 upon L2. So what we will do is, this thing we will simplify, and this thing will become nothing but see f1x L2 minus L1 f2x upon f2x and L2. Okay, modulus of this thing. This thing will be less than what? Mod z1 upon z2 is what? Mod z1 upon mod z2. So this will be less than what? So this will be equal to what? Mod of f1 x L2 minus L1 f2x. Okay, we will before we break it, we will simplify it a bit further. This thing can be written to be what? Because see, we had to bring the results in terms of f1x minus L1 f2x minus L2. So what we need to do is, here f1x L2, what we will do? We will L1 L2 you add, subtract and you add same thing. So this will not make any difference here. Upon this thing f2x and L2. So this is equal to modulus of this thing. Now these two you plug one place, these two you plug at one place. So modulus of this thing, first you write mod z1 upon z2. So it will be the equal to the modulus of numerator upon modulus of denominator, and modulus of numerator is what? This plus this, so it will be less than mod of individual thing. So ultimately see, you will get what? Mod of f1x L2 minus L1 L2 plus this thing here, L1 you can take common rather. So it will be mod of L1 and this thing is L2 minus f2x. Mod of this thing upon mod of f2x and mod of L2. Yes. So this thing again see, I am rewriting right here for you people to explain the things here. Now this is again this simplification here will fetch you what I will write here. Yes, because this is nothing but simplifying this thing. So this is what here you can take L2 common. So L2 mod L2 and then mod f1x minus L1 plus mod L1 and this thing L2 minus f2x mod can be well written to be what? f2x minus L2, because whether you write mod a minus b or you write mod b minus a, that amounts to the same thing. So here this is product of two functions. So mod z1 z2 will be mod L1 into mod L2 minus F2x and mod L2 minus F2x, I will better write to be F2x minus L2. Whole upon, yes, mod of F2x and mod of L2. Yes. So this is all what we will get on simplification. Now see, we have to be wide enough, because this rest of the thing, see what we will do, mod L2, this mod L2 will cancel, okay, here, good. So what you will get, mod F2x, mod this thing, mod of F1x minus L1 here, plus, now here it will be L1 mod L1, mod L2, mod F2x, okay, this much, and then into mod of F2x minus L2. Now this is our A, this is our A. Now see, this whole thing, this whole expression has to be made less than epsilon, and for this epsilon, see, there should be a deleted delta neighborhood of A. So both things we have to switch in, because this expression, what expression, mod F1 upon F2 minus L1 upon L2, this should be less than epsilon. Whenever x falls where? Within the deleted delta neighborhood of A. So that deleted delta neighborhood of A we would be looking for, we would search for. But before we search for, see, this much of simplification we have done of this thing, mod F1 upon F2 minus L1 upon L2. This is practically giving me this A result. Now see, we have to be wide enough. How to get this thing? This has to be this. So what the thing is, since functions are bounded functions, so we will further assume. Now here I am writing, let mod 1 upon F2x be less than m, mod of this thing be less than m, and also L1 up mod of L1 mod of L2 upon mod of F2x, this thing be also less than m. See, this is important. Let these things be less than m. Both these, let m be a number, because these are the bounded function. So let this whole quantity and this whole quantity be less than m individually, because functions are limited. So safely we can assume, yes, there do exist a positive number m, such that this whole thing is less than m and this thing is less than m. Once this thing is being done, then see what we will do. Since individual limits exist, so F1x minus L1 is less than epsilon. So always for this epsilon, you can always find a delta. So here this epsilon, what value you are going to assign? Let epsilon be epsilon by 2 by n. Since limit exists, since limit x tending to a F1x is equal to L1, what does it mean? It means let epsilon equal to epsilon by 2n. So this implies there exists a delta 1 greater than 0, such that what will happen? Yes, mod F1x minus L1, this will be less than epsilon upon 2m whenever what will happen? Whenever 0 is less than mod x minus a is less than delta 1. Similarly, this limit is L2. So what you will find? Similarly, mod F2x minus L2 will be less than epsilon by 2m whenever yes, 0 is less than mod x minus a is less than delta 2. This is equation 2, this is equation 3, call them. So with this, the help of 2 and 3, we put this value in a, so what we will get? Epsilon by 2m, epsilon by 2m, this is less than m, and this is also less than m. So will goes, and you will epsilon by 2 plus epsilon by 2, this is epsilon by 2 plus epsilon by 2, so this is epsilon. So whole thing, that is mod F1 upon F2, mod F1x upon F2x minus L1 upon L2 will be less than epsilon, Mind it, here I will write equality sign, because here earlier see there was less than, this is less than. Yeah, this whole expression here mod F1 is less than, so this will be converted into this thing, so this is how we are going to give the proof of this thing. Now based upon these properties, my request to all my students is that we go through these properties once again, and since they are simple, only the definition here you have to employ, and with this thing we will be now proving a very important result which you have been inadvertently proving this result without knowing the actual proof of it. So now see, When you know the proof, actual proof of the things, then of course see things comes too handy for you people. And see your confidence that increases just like anything. So what our next result will be? Let me have a glass water. Yes, next result is an important result. And that result shows that the limiting value, limit x tending to say p naught of a, this thing, a n x n plus a n minus 1 x raised to power n minus 1 plus, or say a n minus 2 x raised to power n minus 2 plus a1x plus a naught. This is some polynomial of degree n. So its limiting value, what we will show, is equal to is nothing but its functional value. And what will be its functional value? This is our polynomial. So its functional value will be nothing but a n p naught raised to power n plus a n minus 1 p naught raised to power n minus 1 plus a1 p naught plus a naught. This is the result. And this result, so what we have to show, that this is equal to nothing but its functional value, that is a n minus 1 p n minus 1 plus a1 p naught plus a naught. So this is its functional value. So what we are essentially showing is every functional value, that limiting value is always turning out to be equal to be its functional values. So now see here we need not to prove this thing. Only on the basis of our these properties we will prove it. How? Because this thing, what we can write, this is first function, this whole let us assume to be the second function. So limit of the sum of two functions is equal to sum of their individual limit. So what I can well write to be limit x tending to p naught a n x raised to power n plus limit x tending to p naught, and then this rest of the remaining thing, that is a n minus 1 x raised to power n minus 1 plus a1 x plus a naught. And then see, again see what I will do is that a n x raised to power n plus, again that the first term I will take, and the remaining rest of the things from a n minus 2 onward I will assume to be another entity, and again invoking the same result, that the limit of the sum of two functions is equal to sum of their individual limits. What I will obtain is that this is again nothing but limit x tending to p naught a n minus 1 x raised to power n minus 1 plus limit of the rest of the things p naught a n minus 2 x raised to power n minus 2 plus a1x plus a naught. So repeatedly invoking with the repeated iterations, what we will show that all these finite terms individually, see, it will lead eventually to the sum of their individual limits. So ultimately, see, with the repeated iteration, we will get nothing but x tending to p naught a n x n plus limit x tending to p naught a n minus 1 x raised to power n minus 1 plus, and then limit x tending to p naught a1x plus limit x tending to a naught p naught a naught. Now see, one result I did forget to tell you, and that take it for granted right now. We will give there is a small proof of it. That is that limit x tending to a. If f1x is L1 or fx is L1, then limit x tending to a kfx is nothing but KL1. Then see, then if limit of this thing is L1, then this is always KL1. We can prove it where k is any real number, but k is not equal to 0. So this result we will invoke this thing. So here eventually what we will get, that this a term will come outside, because limit. So this thing will be what, see by this theorem, it is a times the limit of this thing. Now an is a constant term, so it is an limit x tending to p naught p raised to power n plus so on, limit x tending to p naught an minus 1, and this thing is x raised to power n minus 1 plus limit x tending to p naught a1 x a1 and then a naught. This is a constant function, so its limit is equal to its functional value. Now one more important result which need to be which we should have derived earlier was this thing, that limit of x tending to p naught of x raised to power n is nothing but p naught raised to power n. How we can prove this result? Quite simple to see, because we have proved another important result, because limit x tending to p naught x raised to power n can be well written to be what? X into x raised to power n minus 1. And because x raised to power n, you can write this thing. And the limit of the product of two function is what? This is equal to limit x tending to p naught x into limit x tending to p naught and p naught x raised to power n minus 1. This is what p naught, because we have already shown that the limit of identity function, limiting value of identity function is equal to its functional value, so it will be p naught. And then this again can be resolved as the product of two function x into x raised to power n minus 2. So again see, this thing will give me what? P naught into limit of x tending to p naught x into limit x tending to p naught x raised to power n minus 2. So this is again giving me what? Same thing, please see. Yes, this result I am writing A. So this is what? P naught, yes, this is P naught into, this is again P naught. So P naught is squared and x raised to power this thing, limit of this thing x tending to p naught x raised to power n minus 2. So again this thing can be broken as x into x raised to power n minus 3. And so the point is that the repeated iterations of the product limit of the product of two functions is equal to the product of their individual limit will eventually lead you what? This thing limit then again see limit x tending to p naught and x into limit x tending to p naught x raised to power n minus 3 and so on. So repeated eventually see what you will get, p naught raised to power n. So this is how we can accomplish the result that the limit x raised to power x tending to p naught x raised to power n is equal to p naught raised to power n. Repeated this thing, product rule. So in effect see, if there is a product of say n function, f1x into f2x into f3x into fnx, so limit of product of all these n functions will be equal to the product of their individual limits of these n functions. So that is a generalization of our product rule of the limit. That is the second property which we have proved here. So with that understanding, see here, now the task is quite simple. Here, this is x raised to power n. So with this this thing will become a naught p naught p power n plus a n minus 1. This thing again will be p raised to power n minus 1 and a1 p naught plus a naught. So eventually see, this is nothing but the functional value of the polynomial. So what we have shown is the important result that the limit of a that the limiting value of a function anywhere in its domain is nothing but its functional value. Its functional value. Okay, so this is all what we had to prove. This is a very important theorem which you had been using in your class 11, but without, I think, knowing the actual proof of it. So with all these things, see, we are now in a position to prove another important result, that this thing. So similarly, suppose there is a rational function. Now what we will show is that if there is a rational function, then the limit of a rational function will again be equal to its limiting value of a rational function will again be equal to its functional value. How? Because what is this rational function? Here you have a polynomial Pmx and here you have another polynomial Qx, and suppose this is a function, this is a rational function, and its limit you have to find it out, say at x is equal to a. So this will be what? This is the limit x tending to a, Pmx upon limit x tending to a qmx, and these are polynomials, so this is nothing but the polynomial of this thing Pma upon qma. So this is another important result which you had been using. Of course, a qmx will not be equal to 0. That is an obvious thing because otherwise your rational function will not be defined. So this is all what we have to do it. Now, one more important result I will be proving here, again making use of that. Two more results which will be, of course, too helpful in your this understanding the things in totality. Will be this two more results I will be proving. So kindly be attentive and have the patience of understanding them, because both the results will be on the basis of your this basic definition, that is the Epsilon delta definition. Their proof will be given. So let us see how their proofs are to be given. So first result is that if f1x, if say fx is less than zx, both functions are having the same domain, fx is less than gx throughout the domain, means they are having the common domain, and your function fx is less than zx, throughout the common domain. Please make use of the word common domain. Then what we will show, that limit x tending to a fx is less than equal to, please remember here it is strictly less than, so it will be less than equal to limit x tending to a zx. This is the important result, and remember that this result you made use of while proving that sine theta upon theta, limit theta tending to limit of sine theta upon theta when theta tends to 0 is 1. You prove this result in class 11 making use of the sandwich theorem. So this is basically one part of this thing, because if a given function is embedded between two functions, say f1x and f2x, and the limits of both f1x and f2x are equal, then obviously the function which is embedded between them, by virtue of this inequalities, will also be having the same limit as that of either of the function f1x or f2x. So here, this let us see how we can prove it. Very simple. And here what you have to assume, that both these individual limit of fx and gx, they do exist. So let limit x tending to a f1 fx is L1 and limit x tending to a gx is equal to L2. I will show you how. And the proof is to be given by what? Contradiction method. Proof by contradiction method. By contradiction method we will be giving this proof. How? Yes. So what essentially we have to show is to show that left hand limit, that is L1, is less than equal to L2. So proof. So let L1 be greater than L2. Let L1 be greater than, suppose this is this thing. So let L1 be greater, so this assumption we are making. Let L1 be, this is our assumption. And we will contradict it. So L1 is, so let this be L2, this be L1. Okay, so when L1 is greater than L2, so what you can do is that let D be equal to, let D is equal to how much? L1 minus L2. And then what you do? You consider an interval D2 less than d2 of both L2 and this thing. So this sum, you are this is d. So let d3 be a number less than d by 2. Let d3 be a number, and this let be L2 plus d3. This mark is L2 plus d3, and this mark is L2 minus d3. Similarly, this mark is L1 minus d3, and this mark is L1 plus d3. So two intervals we have considered. Now see, since individual limit exists, now see, it's too easy for us to show that why this thing will happen. Since limit x tending to fx is L1, this implies for epsilon is equal to how much? D3. For epsilon is equal to d3. There exists, this implies for epsilon is equal to d3, there exists a delta 1 greater than 0 such that what? Mod fx minus L1 is less than d3 for 0 less than mod x minus k is less than d3. Similarly, limit x tending to a gx is L2. This implies there for epsilon is equal to d3, there exists a this thing delta 2 greater than 0 such that what? Here, yes, I am rubbing this thing. Yes, there is a delta 2 greater such that, yes, g mod of gx minus L2 will lie between d3 whenever what will happen? 0 is less than mod x minus a is less than d2. This is 2, this is 1. Okay. Now see, or say d3 only. Take x minus a is less than d3. Here, delta 1, you have already taken delta 3. So let it be delta 4 and let this be delta 5. Okay, because 1 and 2 will exist. Now from 1 and 2, what let delta be less than delta 4 and delta 5 both. So what will happen? Under this condition, what will happen? This fx function will lie here in this interval. Please see, fx will lie in this interval and f2x will lie in this interval. Obviously implying that f to fx is greater than gx, because see, now in this interval, delta interval, in this delta interval 0x minus a is less than delta, what will happen? See, your fx function will lie in the epsilon, this thing, delta 3 neighborhood of L1, and here it will lie in the delta 3 neighborhood of L2. So, and this thing, even the L minus d3 is greater than L2 plus d3. So, since they are lying within this interval, it is plain obvious to see that fx will be greater than gx, which is a contradiction because you have assumed that fx is less than gx everywhere. Fx is less than gx everywhere, and as such, the limit of fx function cannot be greater than limit of gx function. So this is how we will give the proof of this theorem also. And now one more important result you people have to remember at all cost, because that result will be used very effectively when you are finding the derivative of function. That limit, that is a two-line result, and but then of course much do depends upon that how well you have understood this epsilon delta definition. because that is a fundamental definition for proving the results, original results, and their applications. Of course, see, you can do it, but make sure that these two lectures, this lecture and the earlier one on the limits, are too vital for you to understand it. I will be uploading on this channel. Please, students, go through them, understand it, and if any query, please just send me a message. I will explain it to you. So now the second result which we have to prove it, the limit of a function of function. Limit x tending to a f gx, where gx is the internal function and f is the external function. So the limit of this function is equal to what? That we have to understand. So this is nothing but limit, okay, t tends to b. I will tell you what is t and what is my this thing, ft, where see, t is nothing but your internal function gx, and limit of this thing x tending to a gx is nothing but b. This is given, this is given, this is given. See, this is an important result, which see you have still not read, I am more than sure. But the proof, of course, see, you can give very easily by epsilon delta definition, and as such, this result, of course, will help you a lot, because this function of function, derivative of function, you almost use almost everywhere, somehow, in most of the cases where derivative is being used. So this result is a fundamental result, and I will make sure that you have the in-depth knowledge of each and every result as far as limit and derivatives are concerned, because that will form the basis of your basis of your mathematics as well. So please make it sure. Now see how we will prove it. So it is a function of function. I repeat it. It's a limit you have to find at x tending to a. So this is limit t tends to be ft, where t is your internal function gx. And this limit x tending to a of the internal function is nothing but b when x approaches a. So what it means, limit, please see, limit x tending to a gx is equal to b. This implies for every epsilon greater than 0, there exists a delta 1 greater than 0 such that what modulus gx minus b is less than what? Epsilon, whenever what? 0 is less than mod x minus a is less than delta. Here see what epsilon I will be assigning value for every, now I will be assigning value delta 1. Here I have taken delta 1, so delta. So g, here let epsilon be equal to delta. So this thing I will take delta. So gx minus b is less than delta whenever 0 is less than delta 1. Also, so this is result 1. This is result 1. Okay. Also, please see, also limit t tends to be ft. Suppose this is L. This is L. So this implies mod ft minus L will be less than epsilon. So for this epsilon there will exist a, say, delta greater than 0, such that ft minus b is less than epsilon whenever yes, mod t minus b is less than delta. Whenever t minus b is less than delta. Now put the value of t here, so what I will get is mod ft minus L is less than epsilon whenever gx minus b is less than delta. So I would prefer writing this thing. Okay. So, and here at place of t also, see, I will be replacing gx. Okay. Now please see. Whenever this delta. Now here see, there is a trick here. Gx minus b is less than, okay. Now, this is less than epsilon whenever gx minus b is less than delta. Okay, and whenever gx minus b is less than delta, then what is happening? No, x minus a is less than this thing. Here this limit, limit is t tends to b. So what ft minus is whenever t minus b is, so t minus, okay, here see you have to get 0 also. Please see, 0 is the, please see, this correction you have to do it. Ft minus L will be less than epsilon whenever this thing. Now see what the important point is. This is less than epsilon whenever gx minus b is less than delta. Okay, and gx minus b is less than delta whenever x minus a is less than delta 1. So our required delta is what? Delta 1. See, please see. Now result is proof. From 1 and 3 the result is proof. Our required delta is what? Delta 1. Our required delta is what? Required delta is equal to delta 1. You see from here what is happening. See, whenever x minus a is lying in the deleted delta neighborhood of a, that is 0 is less than this thing, then what is happening? Gx minus b is less than delta. And when gx minus b is less than delta, then what is happening? F gx minus l is less than epsilon, so our result is proof. Our result is proof. So because we had only to show that for every epsilon there do exist a delta, and what is our required delta? That required delta is nothing but delta 1. Delta 1. So from equation 3 and 1, our result is proved. Our result is proved. Our result is proved. So, students, this is all what we had to teach you as far as the limits are concerned. Because this is very essential, and if you have understood this much of this lecture and my earlier lectures on limit, I can well assure you that these derivative etc. they will come very handy. I will take one more lectures on telling you the essential points of the derivatives also, that what essentially it means, how the sum of the derivative of sum of two functions is equal to sum of their individual derivative, that product rule, and then that quotient rule. So their proof also we will visit on one of the lectures earlier, and then you will see that this continuity of your class 12 becomes so easy that you almost orally you can try the question therein. So thank you very much. Once again I will upload it by evening because it takes a little bit of time uploading it. So by evening again I will upload it with the hope and expectation that you will learn all these things, whatever has been taught to you in these two lectures. Thank you.